This is a screencast to present to you the information about two-way ANOVA without replication. I attempted to make this for you yesterday, but something happened with the Loom website, and it did not allow me to basically get it uploaded. It's still in the process of saving now many hours later. So anyway, sorry that this is not getting out to you earlier than it did, but one of the things I want you to remember as we're going through this is that when we're talking about ANOVAs, the mathematical machinations that you go through are very much the same. It all deals with sums of squares. Remember that sums of squares is the numerator of the variance function, and when you divide that by the degrees of freedom, that's the mean square, and that's exactly the type of mathematical operation that we used when we were calculating variance. So don't forget that as we go through this. So you might ask yourself why anyone would want to do a two-way analysis without replication. It seems like Dr. Kowinski has been talking about replication all semester, and that's an important thing. But sometimes you're forced with a design of the data that forces you to look at data without replication. It doesn't mean that you can't analyze the data, it just means that it comes with some limitations. And so I want to illustrate this to you by sharing with you an example from my own work. So I used to work in Puerto Rico, and the site that I worked at specialized in studying hurricane disturbances in tropical forests. I worked on ectothermic organisms, organisms that get their body heat from the environment rather than generating it metabolically. This is Puerto Rico getting hit by Hurricane George in 1998, and the forest that I work on is basically right over here on the side of the island underneath the eye of the hurricane. When a hurricane hits an island, hits a forest, the thing that is most obvious is that the canopy opens up. The hurricane comes along, it breaks all the branches fall to the ground, they have all the wood, all the fresh leaves, etc. that was up in the forest is now down on the forest floor. What this looks like is you go from a forest that, if you take a picture of the canopy, it looks like this as you look up towards the sky, and it converts this forest canopy into a canopy that looks like this. And all of that stuff that used to be shading the forest floor is now down on the ground. And so two things happen. You get a lot of this green litter, and when I refer to green litter, it's litter that has not been senesced. When our trees here in Missouri lose their leaves in the fall, they pull back nutrients and energy from those leaves before they let those leaves fall to the ground. Tropical trees do the same thing, and so when a hurricane comes along, the trees didn't know a hurricane was coming along, and so they didn't know to do this, and so all of the leaves that fall to the ground during a hurricane have all those nutrients and energy in them. The other thing that happens is, of course, that the microclimate changes because you now don't have the moderating effects of the canopy. Moderating temperature, moderating moisture. When you get more litter and more nutritious litter, this is going to lead to changes in the energy and nutrients that are available to the organisms on the forest floor. When you get these microclimate changes, you're going to get greater temperature variation and greater moisture variation. These two things are seen, at least temperature is seen in this plot, where you see that in true-fault gaps you have higher and lower temperatures, warmer temperatures during the day, colder temperatures at night, as opposed to the stand that is in blue, showing you that the temperatures are more moderate in terms of their swings. And these two things lead to, in the case of green litter deposition, greater prey supply potentially for insectivorous lizards, and it also alters the thermoregulatory opportunities because you have hotter days and cooler nights, and that affects organisms that are ectothermic. So this is the island, this is the Lucio experimental forest over here on the east side. I work at a field station that is approximately where this black box is. Give me a minute while I get a pointer up here. And for whatever reason, it's just not functioning. Okay. There are four lizards that I concentrate on. One is Anolis gunlocki. This is a forest trunk anole. It lives in full canopy forests, more common in primary undisturbed forest. It's a dark forest kind of lizard. Anolis stratulus is a smaller lizard. It lives up in the very tippy tops of the trees, up in the canopies. It's referred to as a twig anole, and so you're going to find it most commonly if you climb trees. Anolis evermanni is a species that lives in light gaps in the forest. So if a tree falls over and creates a patch of light, evermanni will migrate to that area, so they have higher body temperatures, tend to not do as well in closed canopy forest. And the same thing for Anolis krugi, which is a grass anole, which once again, the only place that you see grasses in the forest for the most part are in light gaps. So we have two closed canopy forest species and two kind of open canopy forest species. And so when a hurricane comes, you might expect these things to change in abundance and distribution. And so after Hurricane Hugo in 1989, Reagan recorded declines in Anolis gunlocki, the closed canopy trunk anole, and changes in the distribution in three-dimensional space of the canopy species Anolis stratulus and Anolis evermanni. But they only followed this for 1 year after the hurricane, and also this was just a typical hurricane where you got the changes in litter and the changes in microclimate all happening at the same time. So we decided that we were going to try and decouple these two major drivers, the effect of litter on the ground and the effect of canopy opening. And so that was what the canopy trimming experiment was designed to do, to decouple the effects of detrital addition and microclimate changes that result from canopy opening after a hurricane. So what was involved? Well, we took a regular forest, like this forest right here, and we basically had one set of plots that we left alone, full canopy, a healthy litter layer, and then we went to another set of plots and we hired some arborists and they cut the canopy out of the forest and we dropped it straight onto the ground after weighing it. And then in two other plots, we took one plot and cut the canopy out, but rather than dropping it down to the forest floor here, we basically transported it to another set of plots where the canopy was intact and dumped all of that litter there. So we basically have normal forest, which is the control. We have a trim and detritus addition, which is kind of like what happens in a normal hurricane. This is a situation where you have the effects of microclimate changes due to canopy opening plus the input of healthy, nutrient-rich litter to the forest floor. Then we have a cut plot with no detrital addition and an uncut plot with detrital addition. So this allows us to separate these two factors from one another. What's the effect of just changing the microclimate? What is the effect of just adding a bunch of nutrition to the forest floor? Now, these are big plots. They're 30 by 30 meters, and this is the field station and the area around the field station. These are the buildings over here. These are trails going out to these plots. And these plots were all put on ridges, the tops of hills, essentially, in the forest rather than down in stream bottoms. And we can't do anything here because this is a large permanent vegetation dynamics plot. So we had to station these plots around the forest. And so these plots went into 4 spatial blocks, Block A, Block B, and Block C. You see that within each of these blocks you have a control. You have a trim with no detritus, you have a detritus with no trimming, and you have a trim and detritus plot. Here in Block B you have a control, trim plus detritus, detritus only, trim only. Block C you have detritus only, trim and detritus, trim only, and control. So each of these spatial blocks, for one thing, they're located at 2 different elevations. There's upper elevation sites and then 1 lower elevation site. And they're also found on different ridges, and so there may be variation from ridge to ridge that is important. So in this case, we have 3 spatial blocks, and we have 1 representative of each treatment in each block. This is the very definition of an unreplicated design. If it was a replicated design, we would have like 3 versions of the control on ridge B, 3 versions of the control on ridge C, 3 versions of the control on ridge A, 3 versions of the trim plot on A, 3 versions on B, 3 versions on C. But we just don't have that kind of space, and so we're forced into this unreplicated design. We did this for a really long time and analyzed a bunch of data. We also have this problem when, let's say, for example, that you're a biologist and you do cell culture. These are pictures of cell culture plates, and you see that, well A1 is not independent of well A2 and B2 and B1. Things that are affecting one of those cells will affect others of those cells. So this plate may behave differently than this other plate in an incubator, for example, because all of the things on there are linked together. And so you can treat this plate as one block, this plate as another block, this plate as another block, and this plate as another block. Now, if you have a bunch of different treatments, you may not be able to replicate within this block. And as a result, you won't have any replication of your treatments within this block. And so this would represent another situation in which you have an unreplicated block design. Other ways in which you might have unreplicated designs are in business, which we'll see in a few minutes. We're going to look at some economic data. So here are the formulas for a two-way ANOVA without replication. You have treatments, you have the effective blocks, you have a residual term, and you have the total. And what you notice in this is you don't have any interaction term. And the lack of within block replication basically prohibits you from calculating a interaction term. Now there's ways of assessing interaction, which we'll see when we get to some actual data, but you can't put a p-value on that. You can't put an F statistic on that because it just doesn't appear in the model. Once again, we see that this is just the sums of squares. It's the mean of the treatment minus the grand mean squared, summed up across all the treatments, and then multiplied times the number of blocks that you have those treatments distributed across. The block effect is the mean of the block minus the grand mean squared times however many treatments you have in each of those blocks. The degrees of freedom are over here. And then the residual term is easiest to calculate once again by calculating the total sums of squares and then subtracting from that the block effect and the treatment effect. But here's the equation if you want to try and do it in another way. In this case, the total sums of squares is each of the individual values regardless of treatment and block minus the grand mean squared, added across all treatments and added across all blocks. And once again, that's the total sample size minus 1 is the degrees of freedom. So let's say that you have a supermarket, a set of supermarkets, and you're interested in, let's just say, the cost of toilet paper across these supermarkets. But what you're really interested in is are brands differently priced? And so we have brand A, brand C, brand A, brand B, brand C, and brand D. And we have this in 10 different supermarkets. Let's say one of these supermarkets is the Hy-Vee off of 152. One of these is the Price Chopper off of 291. One is the Price Chopper at I-35 and 291 north of here. Another one is the Aldi across the way. Another one is the Target. One is the Walmart, etc., etc., etc. Well, you only have one Hy-Vee at that location. The 4 brands are going to all be represented there, but you don't have 2 Hy-Vees sitting right next to one another that would represent replication. While you may have a Price Chopper over off of 291, kind of southwest of campus, that's a different Price Chopper than the Price Chopper that is up off of I-35. One of them is newer, one of them is in a set of new, surrounded by a set of new subdivisions, one of them is much older and surrounded by older housing, and that might affect price of brand A, brand B, and brand C of toilet paper. So these represent blocks. The supermarket represent blocks, and the brands are the treatments, and there's no within treatment variation here. So the residual variation comes from a different place, and that's the important thing to recognize. So the first thing we want to do is calculate the means of the treatments and then the means of the blocks. And so this is the mean of brand A across all 10 grocery stores. This is the mean of grocery store A across all 4 brands. From this, we can then calculate the sums of squares columns, but this is a different way of calculating the sums of squares. We basically calculate the grand mean, we subtract the grand mean from the column mean, square that, and that's what this number is. Column mean minus grand mean squared, that's what this number is. Column mean minus grand mean squared, that's what this number is. Column mean minus grand mean squared, that's what this number is. Those then get weighted by the number of stores, of grocery stores, supermarkets, over which that mean was arrived at. So you would multiply that times 10. So if you just add these 4 numbers up, it comes to 0.005, but when you multiply times 10, this value is 0.5. And go back to the equations, and once again you see that the treatments are the treatment mean minus the grand mean squared times the number of blocks, which is Q. So you do the same thing with the row means. Row mean minus the grand mean squared is this number. Row mean minus grand mean squared is this number. Add all of those up, and you would multiply that sum times 4 because these row means are the averages of 4 different brands. So now you have the sums of squares for the supermarkets, sums of squares for the sums of squares for the supermarkets, sums of squares for the brands, and you can now calculate the sum squares total by basically taking each individual data point, so the price of toilet paper for brand A and supermarket A minus the grand mean squared plus A versus B minus the grand mean squared, AC minus the grand mean squared, AD minus the grand mean squared, AE minus the grand mean squared, AF, etc., etc. That leads to a big matrix of squared deviations from the grand mean, and you sum this whole thing up, and it gives you 0.00485. So now you have all of these things that you need: the sum squared error, and the sum squared residual, the sum squared residual, the sum squared due to supermarket, the sum squared due to brand. Those 3 things should all add up to the sum squares total. Degrees of freedom for brand is 3 because you have 4 brands. Degrees of freedom for supermarket is 9 because you have 10 supermarkets. 3 times 9 is 27 for your residual degrees of freedom. That all added up equals 39, and you have 40 data points total. And then once you have these numbers, the degrees of freedom and the sums of squares, it's all just the same math that we've used before. Mean squared is sum squared divided by degrees of freedom. You get the mean squares. The F statistic for brand is the mean squared brand divided by mean squared residual, which is 92.7. Mean squared supermarket divided by mean squared residual is 107.9. And both of these things are super duper significant. And so, once again, it's just the same mathematical operations, means minus grand mean squared. It's just that the means that you calculate, or this deviations from the means that you calculate, are slightly different than what you would do in a replicated version, because you have to calculate, for example, residual sums of squares somewhat differently. When you plot this out, you would see that brands A and D seem to be lower than brands B and C. If you just average brands across all the supermarkets, but you also see that there is an effect of supermarket in that you really want to be shopping at supermarkets C, E, and J rather than supermarkets I and G, because they have the highest prices on average. And so when we look back at the ANOVA table, there was an effect of brand and there was an effect of supermarket. And you see this by looking at averages of brands across supermarkets. And you can see this in looking at the averages in supermarkets averaged across brands. And what you can't do is you can't get a sense of what the interaction is. Now, in R, you can get it to calculate the means where you have both brand and supermarket as the main effect. So you can do a summary SE on brand and supermarket looking at price. But what it's going to do is it's going to give you an error message that says that there are a bunch of NAs in your new data frame because it can't calculate confidence intervals because there's no replication. But you can still do it, and it'll give you whatever it can. And when you plot that, it gives you how brands vary in price across supermarkets. But what you notice about each of these points is that there's no error associated with them. It's just plotting the data points. But you can evaluate whether you need to think about interactions by looking at this type of plot, because what you see is that as you move from supermarket A to supermarket B, brands A and D are lower than brands B and C. And that stays true for every supermarket in your sample. Not only that, B and C change positions slightly, but there aren't any big shifts in the prices of those two brands relative to one another. And the same thing is true of brands A and D. They follow the same pattern and they don't change position. In most cases, brand A is slightly more expensive than brand D, regardless of which supermarket you're in. And when a plot looks like this, you can say, well, there really isn't much interaction because these lines don't really cross one another very often. So it's not a quantitative assessment of interaction, but it's a qualitative assessment of interaction. And if you saw a lot of crisscrossing of these lines, then you would say, oh, there's some interaction going on there, even though we can't quantify it. Next time we meet, we'll go through this, answer any questions that you have about this, and then we will actually start showing you how to do these analyses in R. Thanks for tuning in, and email me if you have any questions.